So first of all, I would like to thank all my colleagues that is being part of this webinar, Christophe and Ongwai, that are really a pleasure to work with you. And also I really would like to thank the studium, especially Maureen, that do so a great job on this organization. And if it's possible to do this webinar today, it's fully her job. So really thank you, Maureen, again. So today I will present some of our work dealing with natural deep eutectic solvents, of course, but using it for microalgae biorefinery, and especially to show you that the use of this NaDES in multi-step processes to see how we can build this multi-step processes using NaDES. So first, I just want to present you our group research. So I'm working in a lab called SIMBA for synthesis and bio-isolation of bioactive molecules, which is a team of 20 researchers with a production of about 10 to 15 publications per year. And our research focused on building and designing alternative solvent and green chemistry processes for organic and medicinal chemistry, and of course for today in eco extraction. And we try to find new molecules for cancerology, infectology, and cosmetology. So in our group, we use NaDES in different ways. So first of all, we have some skills in NaDES design, first using empirical approach, but also we're starting the thermodynamical approach using COSMO-RS, as Mr. Abranches showed us just before. And also we're specialized in designing dedicated processes for biomass extraction and biorefinery, and organic synthesis dedicated to the use of NaDES. And in our lab, we are the owner on a NaDES library, almost more than 150 systems with non-polar and switchable NaDES systems, especially that are compliant with the international cosmetic regulation. So today, the question that I want to explore with you is that, is NaDES a suitable tool for microalgae biorefinery? So we will explore this question with Spirulina as a case study. So why Spirulina? First, because Spirulina, it's a really widespread and well-known microalgae. It's a blue-green microalgae belonging to the cyanobacteria, and she contains a lot of molecules of interest, which are polar, like the blue phycocyanin, which is a phycobility protein, and also non-polar, like the chlorophylls, the carotenoids, and the free fatty acid, especially polyunsaturated one. So for cosmetics, this microalgae is really interesting. So we are working in a project that is called Dermic, starting from the sustainable raw material to design NaDES and to optimize all the process to propose ready-to-use cosmetic ingredients for the market. So we will see briefly the NaDES design first. So in our group, so during the PhD of Laura Wills and the PhD that is currently under investigation of Merve, we are design a library based mostly on the beginning on trial and error, and now with Merve we are also working with a new computational approach using COSMO-RS and working with, of course, Sigma profiles as we see just before. So with the COSMO-RS and the Sigma profile, we can generate the eutectic profile of the mixture, and empirically, experimentally, we think that the eutectic point of this system was here with the ratio of 12.1, but with the COSMO-RS prediction, we found that the predicted eutectic point was a ratio totally different, it's 1.2. And we try to prepare some NaDES in this range. All NaDES was working, and we performed some extraction with all the range, and we don't see any big impact on pigment and FFA content during the extraction. It means that maybe we're not really obliged to be at the eutectic point to perform a good extraction, but we saw for sure a eutectic effect compared to the pure solvent we tested alone, the pure component as solvents, and there is a eutectic effect even if we are not at eutectic point. So this is really interesting, and we are still working on it. So we have the NaDES design performed. We have a huge library. So we then move to the unitary operation optimization. So for first starting with the non-polar compound, free fatty acid and non-polar pigments, we start with frozen Spirulina biomass and screen 20 NaDES. And I will show you the result for 2 NaDES that are also confidential. And we compare with all NaDES, the Ultrason-assisted extraction and new processes that called SIMBA process. So if we compare first the FFA contents, we can see with the 2 NaDES that with the UAE, we obtain good performances, but really less compared to the new SIMBA process. And we screen different data sets with the SIMBA process, the set A and the set B. And we can see with the data set B, we have really a huge improvements of the extraction capacity. This was more significant for the pigments because using the dataset B, we can see that there is a huge, dramatic extraction increase of the pigments compared to the other processes. So it means that we can, with the same NaDES, modular the selectivity according to experimental parameter, which could be really interesting for multi-step processes. Also, if we compare the productivity of the UAE and the SIMBA process, we have a productivity reaching more than 8 grams per hour of FFA, considering the SIMBA process compared to less than 1 gram in UAE, which it means an increase of 40-fold, which is really, we are really pleased to see these results. Working with free fatty acid, we also have to consider the fatty acid profiles in the fraction we obtain. So we compare the fatty acid profile in the fraction resulting after ultrasound. And here you can see that there is mostly saturated fatty acid in the fraction, which is not our main goal, because what the fatty acid of interest at the polyunsaturated one. But with the NaDES and the same NaDES, but the SIMBA processes, we can see that now we have fraction dominated by the polyunsaturated one. So it's a really good result for us because we think that our process preserves the buffet compared to the ultrasound. So during all this work, we identified that fatty acid-based and mantle-based NaDES are really suitable to our purposes, and also that the nature of extracted free fatty acid, depending first, of course, of NaDES composition, but also on operating composition. So we move then to polar pigments, and especially phycocyanin, and this work was performed during the postdoctoral fellowship of Sokaina Ilali. So we screen almost 60 different NaDES. We can see here the different color of the extract obtained, and we select 5 NaDES that performed the best performances. So it was all glycerol-based, and then we use these 5 glycerol-based NaDES versus water as a reference for ultrasound extraction, optimized by RSM, and then we have some bad generic conditions that were highlighted. It was 30 to 40 degrees maximum for the temperature, 20 to 30% of water in NaDES, and 60 minutes of extraction. The main point with the phycocyanin, the main problem was the stability of this protein in solution, especially with temperature. So we submit our extract to accelerating aging during 1 month. And then we are really delighted to see that even if the water extract be totally exempt of phycocyanin, it was totally destroyed. You can see the yellow color. In glucose glycerol NaDES, we can see that we still kept this blue color and the phycocyanin was preserved. It's really interesting. It means that the NaDES containing glucose especially are really good stabilizer of this protein in solution, could be a good way to improve the use of this phycocyanin in the industry. So we optimized the unitary operation, and now we are currently working on the biorefinery, mean on multi-step processes. The main challenge we have is that we want to use only NaDES during all this biorefinery. So we explore two different approach, a sequential one and then a biphasic one. So to illustrate these two approach, I select today a couple of two NaDES, a polar one, the glycerol glucose, and a non-polar, the maltol lauric acid. So first, we try the sequential use of NaDES using UAE. So we wanted first to use this scheme. It means that we wanted to start with non-polar extraction first, because it was really easier to recover the non-polar NaDES and to separate it from biomasses compared to the polar one. So we have a lot of faith in that, but it didn't work at all, because the first step was working, of course, but after that, the biomass was no longer possible to extract with the polar NaDES. So we tried the other sequences, polar, then non-polar, and this time it works. So we keep these sequences and we optimize it. So we apply this sequence polar then non-polar with glycerol glucose first, and then mannitol C12. And if we have a look on non-polar metabolites, if we compare the sequential extract here, non-polar extract here, to the reference monophasic extract optimized in unitary operation, we are really disappointing at the beginning to see that we have a dramatic loss of performances for the extraction. And the reason is really simple, is that because the glycerol glucose, our polar NaDES, are really good at extracted non-polar compounds, which are not really what we are wanted, but it's like that. So we decide to add a liquid-liquid extraction step of GG extract using the NaDES. And we have absolutely no clue at the beginning if it was working or not. So we keep the same scheme, and we had an additional step of liquid-liquid extraction of the polar GG extract using mannitol C12 to generate a purified polar fractions and a non-polar fraction that was pooled with the non-polar extract, resulting of the second step extraction of the biomass. And if we have a look on non-polar pigments, we are really delighted to see that we recovered almost the same amounts with the pool fraction compared to the reference extraction. It means that our liquid-liquid step worked really well. That is also visible in considering the polar extract, that we have a dramatic decrease of non-polar pigments in the purified polar fractions. So this is a proof of concept that this liquid-liquid extraction with NaDES could work. If we have a look on phycocyanin, because we have also interested in phycocyanids, the rates were almost the same. We have a slight loss after liquid-liquid extraction, but it's just because we lost some NaDES during the process. But there is another fact that is remarkable, is the color of the fraction. Before liquid-liquid extraction, the glycerol glucose extract was green-blue due to carotenoids and chlorophyll combined with phycocyanin. But after liquid extraction, since the other pigments are almost removed, we restore the bright blue color of phycocyanin, which is the desirable color we want for the fraction, because it was really difficult to obtain this blue color naturally, and it's really interesting. Look at now at free fatty acid. So again, we can see that with liquid-liquid extraction, we restore almost fully the FFA amount in the pool fraction, and we really purified the glycerol glucose phase of free fatty acid. So the recovery here is almost 85%, which is a good result. So we are really proud of this liquid-liquid step that really improve our product, but the time is really long. So we think that maybe we can try something a little more crazy. It means that we can start directly with a biphasic ultrason-assisted extraction. It means that this time we introduced frozen biomass, glycerol glucose, and menthol C12 NaDES in one step at the beginning, and then perform the ultrason-assisted extraction, only one step of extraction, then centrifugation, and we hope that we obtain directly a purified polar extract and an enriched non-polar extract. So when we take the tube from the front centrifuge, we obtain this kind of tubes with the non-polar fraction at the bottom, the biomass in between, and the polar fraction on top. And if you have a look on the polar extract, it's already bright blue, so we guess it works. It was already purified. The polar content was almost the same compared to the reference. So for the phycocyanin, it works. We have similar phycocyanin content and a bright blue color in one step. If we have a look on non-polar pigments, again, we have a polar extract that is almost free of non-polar pigments, but for the non-polar NaDES, non-polar fraction here, we can see that we have a slightly improved performances for non-polar pigment compared to reference. And also it was easier using this biphasic approach to recover both non-polar and polar NaDES. So for us, it's really a good results. Considering FFA, it was also like that. We have improved performances compared to the reference with a 106% recovery of free fatty acid compared to the reference. And also we can show that we really purified the polar fraction compared to the reference GG. So if we compare the two approaches, we have a global extraction time really decreased using the biphasic approach, using almost 3 times, and that's of course led to increase of productivity. And also for just using in the lab, the NaDES phase recovery was really tedious using the sequential liquid-liquid approach, especially with polar NaDES. But with the biphasic approach, the biomass act as a separation layer that was really well defined, and then it was really easy to recover both non-polar and polar NaDES. If we consider the phycocyanin content, the performances are almost the same, but in one step for biphasic extraction and with 2 steps of extraction for the liquid-liquid, so the productivity is almost double for the biphasic extraction, and we restore in all cases the blue colors. Looking at now non-polar pigments, so the performances for polar phase is almost the same. We say really slight amounts, but for the non-polar, we saw that we have increases performances using biphasic approach that are really amazing for the carotenoids. It means that 122% of increase compared to the pool fraction, which is really interesting because the carotenoids are really compound of interest. And for the chlorophylls, it's only 20% of increase, but it's not so bad. If we compare then the productivity for carotenoids, with the sequential approach, we are almost 20 milligram per hour, but more than 130 per milligram per hour was the biphasic. It means an increase almost 7-fold, which is a really amazing results. Looking at FFA, again, we can see that the performances are really increased with using the biphasic extraction for non-polar NaDES compared to the pool fraction and sequential approach. The productivity, again, is really improved a factor 4. Then reaching 2 grams per hour using the biphasic approach and 0.5 grams per hour using the sequential one. And if you have a look on the composition of FFA fraction using the sequential approach, we again see that we have a huge saturated fatty acid amount in the fraction, which are again not desirable in our case. But using the biphasic extraction, we restore a huge amount of purfate and murfate, and saturated are really decreased. It means that maybe using the two NaDES will preserve the purfate from ultrason degradation. So as a conclusion, the NaDES design, dedicated design for the microalgae was okay. We have optimized system for both polar and non-polar metabolites. And also we have some system that can act also as stability enhancer. For the unitary operation, we have optimized it for the both compounds, but we can see that with the new SIMBA process, we have a full power of the NaDES that are really allowed to work. And the selectivity and the stability of the extraction were really NaDES dependence. And also we highlight was we have some polyvalent extracts. It means like for GG, we have some NaDES that are able to extract both polar and non-polar compounds that could be also interesting for some application. For the biorefinery, now which was our main concern, we can prove with this work that it's feasible to use NaDES, only NaDES in the biorefinery scheme, even on sequential and biphasic approach. But in our point of view, the biphasic was the more promising one. And also it could be possible to purify the polar fraction in one step with the extraction. This is really interesting. And at the moment, we are also working on formulation to introduce this extract in a cosmetic formulation to see the compatibility of this extract with the product. And for the first results were really promising. So I would like to thank all my students, all my colleagues, all my collaborators, and of course, all the funders that allowed this work to be done. And I would like to take just 5 seconds to present you a special issue that I'm a co-editor in Frontier in Chemistry, dealing with the application of green chemistry for biomass valorization. And of course, green solvents are considered. So if you have any works that you would like to publish with NaDES, you can feel free to submit it. The abstract are due to 3 of October for the abstract and the full paper for the 3 of December. So thank you for your attention.